My name is Dustin. I'm DI on GitHub. I work for a company called PropWorks, which is based in Philly. We have some offices in Austin and New York too. I'm the director of the Austin office. And my talk here for you today is called The Fastest FizzBuzz in the West. So a quick disclaimer, this talk is not actually about FizzBuzz. However, FizzBuzz is kind of like the faux motivation for this talk, right? So to get started, I have to actually explain to you what FizzBuzz is. So FizzBuzz is like a really elementary programming problem, right? I've never been asked to do this in an interview, but it's commonly used in interviews. And it's something like this, right? You write a program that prints the numbers 1 through n. If it's divisible by 3, you print fizz instead of buzz. If it's divisible by 5, you print buzz instead of 5. And if it's divisible by both 3 and 5, you print FizzBuzz. That's FizzBuzz. So at various stages of my career, I kind of like always imagine what would happen if someone asked me to do FizzBuzz in an interview, right? So like very early on when I was learning Python, I might write something like this. This is like super normal, super naive FizzBuzz implementation. It iterates over the numbers from 1 to n plus 1 and checks the modulus of the numbers and prints FizzBuzz, FizzBuzz, or just the integer, depending on if it's divisible or not, right? And this is totally fine, right? This works. It prints FizzBuzz. It looks like this. But then I got like really kind of fascinated with this. Like I was like, I really want to like demonstrate my skills if I was ever asked to do this. So then I memorized this thing. I got really into like super terse programming. And I memorized this random function that actually also implements FizzBuzz. But in my imagination, there was like no limit to what the solution could be, right? Like maybe it could be in a different language. It didn't have to be Python, right? So I thought maybe I'll really like wow this interviewer. I'll learn Fortran and I'll implement FizzBuzz in Fortran, right? People still use Fortran, right? What about this language? That'd be really funny, right? And really, there's no limit. So as great as all of these would have been for my hypothetical interviews, I never bothered to learn Fortran or any of those other things. But it still really intrigued me. Like, where could I draw the line with FizzBuzz? Could I actually make my own language and use that in the interview? So I did. I created a language called DivSpill, which stands for Dustin Ingram's very special programming language. And since it's my own language, I can make the syntax whatever I want. So let's just make it the bare amount of information necessary to implement FizzBuzz, right? We need to know what the range of numbers we want to print is and what we should replace one number with if it's divisible. So it's 1 to 15, fizz is 3, buzz is 5. Done, that's FizzBuzz implemented. So my goal for the talk is to show you how you can take this syntax and turn it into something that does solve the FizzBuzz problem. And I want to quickly say that like this whole thing is on the shoulders of giants, right? I didn't start from scratch and write a language. There's lots of tools available to you that you can use to write languages, and they're all of various circas. So the earliest ones are Lex and Yak. And then there's a tool called Ply, which David Beasley, who's here actually, he wrote. And then there's another tool called rply, which Alex Gaynor, another Python developer, wrote as a re-implementation of Ply. And so I'm going to use rply to implement this language. And rply, just a quick note, it runs on something called rPython, which is a lot like Python, but it's kind of restricted. And I just want to point out the differences between rPython and Python real quick, because it's going to explain why things look a little bit weird later. So Python is dynamically typed, right? I can have a variable that's a string, and then I can change it to an integer. Python doesn't care. I can also have a function, right? The function takes an argument, and maybe it returns a string, maybe it returns an integer. It doesn't matter. But in rPython, which is mostly used for defining languages like Python, it restricts the ability to mix these types in arbitrary ways. So while the normal Python interpreter would just gladly say, yeah, okay, like sometimes I'll give you a string, sometimes I'll give you an integer, in rPython this would be like a big blow-up error. You couldn't even run it. So if you see me doing some like kind of weird Python later, this is probably why. So let's design a language. And first, I want to show some parallels to written human language and then sort of draw some similarities out of it. So let's say that I show you this string. And let's say I'm actually going to reveal it to you one character at a time. And I need to tell you, like, you need to interpret a sentence from this. So maybe you start with the letter I, and you're like, OK, that's the word I. And then is not a word, so maybe is space And you go along until you get to the very end, and you say, oh, wait, that doesn't parse correctly. This sentence must be, I saw a man. And so luckily, we have spaces. And this helps us disambiguate the characters in our language into words. So I can look at a sentence like, I saw a man eating chicken, and I don't need to like break it up into chunks. And so if we were to sort of parse this into a list of words, it would look something like this. And so the spaces and the characters are tokens in our language. That's what makes up the sort of the stream of a language. But we also have like expressions in our language too, right? And if you think back to like elementary school when you're diagramming a sentence, you would do something like this with this. You say, I saw what? I saw a man. I saw a man doing what? I saw a man eating chicken. And you would sort of group each one into a logical thought. And this is what you would think or see in your mind when you evaluated that sentence. But this can be ambiguous, right? So it could be, I saw a man eating chicken. Or you could group this slightly differently. And you could say, I saw what? I saw a man eating chicken. And you would see this in your mind too, right? So the result is kind of ambiguous, and that's why we have even more additional characters. So I can put a dash between man eating, and then it's very clear to you what I'm trying to say here. So steps to interpreting a language. First, we're gonna break our stream of characters into tokens. And this is when we took the individual letters and turned them into words. And then we're gonna combine these tokens or words into expressions, which sort of draw some meaning towards us. And then we're gonna evaluate these expressions into like one final sentence, one final image in our mind. So let's talk about some types of tokens that we're gonna have in DivSpil. So the first is gonna be numbers, and this is gonna be any like numeric character in a group. So they would be 1, 15, 3, and 5 here. We're gonna have periods, but I'm gonna say that 3 periods in a row is called an ellipsis character, and it's gonna represent the range. We have things like that are strings, which I'm going to call words, like fizz and buzz. This is what we're eventually going to replace the integers with. We have the equal symbol, and maybe we have white space too, right? So the next step is to make a lexer. The lexer is kind of simple. All it does is take this continuous stream of characters, and then it gives you an iterator that you can just call next on over and over again and get a token from your language. So if I gave it a stream of characters, it would give me either a number or a word or an equal symbol, one of these tokens from my language. So from rply, I'm gonna import a lexer generator. I'm gonna initialize it. And then I'm gonna start adding named tokens. And these named tokens are basically gonna be regular expressions. So the ellipsis token, I'm gonna call it ellipsis, and it's gonna be 3 periods in a row. So anything in our stream of characters that matches that is gonna be an ellipsis. Similarly, numbers are any repeated digits. Equals is just the equal sign. A word is any lowercase a through z 1 or more times. We're gonna ignore white space because we're super cool, and we're gonna also ignore comments because we're good developers. So a comment is gonna be anything between, just like in Python, a pound and the new line character. We're gonna build our lexer, and then we have this like lexer object, and we can give it a stream of characters. And like I said, we can call next on it. So the first thing in this stream is going to be the ellipsis. So we get back a token, which is an ellipsis, and we get back the value for it too. We can call next again, and we'll get foo. Next again, 42. Next again, and we get hut. And so if our stream has invalid tokens, right, our language doesn't know how to interpret them. So if I put an exclamation point in here, that's not like in any of the regular expressions that I defined. So this works for as it consumes tokens, as it consumes words that it knows how to reason about, until it gets to the invalid character. And it says, this doesn't match any token that I know about. This is invalid syntax, right? So if I were to lex the entire DivSpil program, which is the 1.15, fizz equals 3, buzz equals 5, and again, like white space is stripped here, so it can just all be one string, we get a list of tokens. And each of these lists of tokens represents all the like pieces of our language. So that's the first step. We take the lexer, we break the characters into tokens. The next step is to combine tokens into expressions. So again, like we grouped characters into tokens, we're gonna group tokens into expressions. And to do this, we need to make a parser. A parser that we're gonna specifically be a look ahead, left, right parser, but you don't really need to know what that means. It just means that it's gonna take this token stream, this list of tokens from the lexer, and it's gonna separate them and analyze the tokens according to some rules that we're gonna make up. And this set of rules is what's normally called a formal grammar. It's the grammar of our language. So let's define our grammar. Here's our normal FizzBuzz or DivSpil implementation. So we're gonna draw some boxes around the different types of tokens and expressions we can have. The first one I'm gonna say is an int box. These represent our integers. Similarly, word box represents streams of alphabetic characters. And then I'm going to sort of group these tokens into bigger boxes. So here's a range box. It represents a integer, and then the ellipsis, and then another integer. And similarly, I'm going to say these are the assignment boxes. And then I need to group all of the assignments together. So the assignments plural box is going to group multiple assignments one after another. And finally, I need an expression that I can evaluate just to get the result of the entire program. So this is going to be, we're going to call it main box. And it's just everything that represents a valid program. So it needs to include the range at the beginning and then any number of assignments after it. So altogether, it kind of looks like a mess like this. I mean, you can sort of think of it as a parse tree, right? A main box is built up of a range box and an assignments box. Range box has 2 int boxes in it, et cetera, onwards and onwards. So we're going to define our boxes now. So first is the int box. And from rply, we're going to import what we call a base box. It's a box that doesn't know anything at all. And we'll subclass this into int box. When it's initialized, it gets a value. This value is whatever was those characters in that stream at that point that it recognized as matching that regular expression. And then we're going to add an extra function to this. It's going to be called getInt. And all this does is take the value and coerce it to an integer. Keep that in mind. So I can initialize an int box with a token. And when I call getInt on it, I get the integer 1, not the string. So next, the range box. The range box is going to take 2 arguments, low and high, and then we're going to define a function called getRange on it. And getRange is going to return the Python range function, which is going to be a list of integers. So in the same way, I can initialize a range box, and when I call getRange, I get the numbers from 1 through 15. Next is a word box. Again, this is kind of like the integer box, except we don't need to coerce it to an int. It just returns the string that was the word. So if I initialize a word box with a token that is a word and has the value fizz, I just get fizz when I call getString on it. And now it starts to get a little more complex. So this is an assignment box. It's going to take a word and a number and store that when it's initialized. And then I'm going to write this function called evalWith. And it's going to take an integer. If that integer is not evenly divisible by the number that I initialized it with, it returns an empty string. But if it is evenly divisible, it returns the word that was in the assignment. So if I initialize an assignments box with a word box that's fizz and an int box that's 3, and I call eval with the number 40, 40 is not divisible by 3, so I just get an empty string. But if I call it with a number like 42, I get the value fizz. The second to last thing we need to do is an assignments box. This allows us to repeat assignments over and over. So what this does is it contains a list of assignments, and it just appends them all into one list. So when I eval a plural assignments box, I just get back the list of all the assignments that contain it. So it looks like this. Assignments box, you can give it an assignment, and I can call getList on it, and I can get back the list of all the assignments in that box. And I can repeat this, so if there's 2 assignments, they're sort of nested within each other. GetList on the outer assignments box gives me all the assignments inside it. So the last thing is the main box, and this is how our program runs, right? We have to evaluate the topmost expression, which goes and evaluates all the expressions underneath it. So this is going to take a range box. We're going to say that comes first, and then a list of assignments. And then this is kind of the meat of the divspell program, right? It's going to create this range, and it's going to iterate over all the numbers in the range. And it's going to build up a line for each number. The line at first is going to be an empty string. And then it's going to go over all the assignments that we've defined in our program. So if I've assigned fizz to 3 and buzz to 5, it's going to iterate all over those and call evalWith on that assignment. And if the number is not divisible by that number, it gets an empty string. But if it is, it gets a word back, like fizz or buzz. And eventually it concatenates all these together into a line. And at the end, if the line is empty, we just turn it into the integer. And if it's not empty, we leave it as is. So that's how we get fizz, FizzBuzz, or just the number. And in the end, we join it all with new lines and return it. OK. This is probably pretty hard to see, so I'm going to skip it. But again, we basically define every box that makes up our program, and all of it is contained within the main. So the last thing to do is define productions, which is what we're going to do to take a pattern of tokens and turn it into one of our boxes. So again, here's our application. I'm going to say that the range is the number followed by the ellipsis followed by the number program. Assignment is a word followed by the equals sign followed by a number. Assignments is sort of like a recursive. It contains any number of assignments plus an additional assignment. And it could be just no assignments at all. And finally, our main program is, our main production is a range followed by a number of assignments. So we get the parser generator from rply and we initialize it with the list of all tokens in our language, which are ellipsis, equals, number, and word. And then I start to define productions. So this is the number production. All it does is return an int box. This is the word production. All it does is return a word box. And then we have to define productions for each of these other ones too, right? So a range, number, ellipsis, number. This receives an argument p, which is the list of the tokens. So we're going to throw away the ellipsis. We don't actually need it to evaluate an assignment. But then I'm going to initialize a range box with the number and the low number and the high number. Similarly, here's the assignment. Multiple assignments is just going to return assignments box. For an empty string, it just returns an empty assignments box. And here's our main program. So the main is going to take a range and assignments and return a main box. All right, so here's our parser. We build it. And then we can parse things, right? So first we can hand this string to our lexer, and then we can hand the stream of tokens to our parser, and we get that main box object that I created. And when I call eval on it, I get this string back, right? So we've evaluated the entire program here, and it's printed out every integer in the range from 1 through 15 with no assignments. Okay, so the last thing that we need to do is evaluate the expressions. And this is a job for our interpreter, right? The interpreter takes the stream of tokens, it evaluates it, and then like in Python, it prints it to the console, right? So this is like a really rough approximation. We're going to initialize our lexer, initialize our parser. We're going to assume that the first argument is a file name, and we're going to open it, and then we read the source, which is just the stream of tokens. We hand the source to the lexer, which that produces the stream of tokens. The parser parses the tokens and creates an expression, which is our main box. We evaluate the expression, and then we print the result to the console. So that's it, we've done it. So let's review real quick. So what we can do now is write a file, fizzbuzz.divspill, or whatever you want to call it, which contains something like this. You could pip install divspill. And you can call the executable divspill on the file, and then you get FizzBuzz. So we took this syntax, we turned it into this stream of tokens. That was evaluated into, or that was parsed into this set of expressions. And then when we evaluated, we got this string, which the interpreter took and printed to our console as a valid FizzBuzz. So now let's take it one step further, right? This is the initial FizzBuzz problem. Numbers 1 through n, 3, 5, FizzBuzz. Well, let's say like I'm a really tricky interviewer and I want you also to, for every number divisible by 7, print fuzz. And so that really complicates things, right? Because if it's divisible by 3 and 7, you have to print FizzFuzz. If it's 3, 5, and 7, FizzBuzzFuzz. And so when we look at this like super naive program that I wrote at first, it like blows out of proportion because I have so many more cases to test for all the different divisibilities of 7. But in divspill, all I have to do is increase the range to a number that's a lot higher and add one more assignment, and then I can run it and it will just interpret it the same way. It'll print FizzBuzzFuzz. Okay, so some questions that I'm expecting now. And the first one is, why would I ever use this? So it kind of depends on what you're talking about, right? If you're talking about divspill, obviously it's kind of only good for one thing. So if you're ever in a job interview, I would encourage you to try and use it, see if it works. But really, maybe you're asking like, why would I ever want to make my own language? And you know, like Python is pretty good, right? Like why do we need more languages? And I didn't have a great answer to this because other than like, you know, you'll know it when you see it. But I was just in James's talk, and James is the creator of a tool called JamesPath, which I learned 2 things about. First, it's pronounced JamesPath, and that means he named it after himself, which obviously, as someone that made a language called divspill, I approve of that. But also, it uses something called a JamesPath expression, right? So JamesPath allows you to parse and interpret JSON. So if you import JamesPath and you give it a dictionary, you can say something like foo.bar, and you can sort of traverse into the dictionary and get the value out of it. Yeah, so this is the tool JamesPath. And he's not using like rply or ply or anything like that, and I don't really know enough about the tool to say if he could, but this is a really great example of a time when you might want to create your own language. And when I look into his repo, he's got like, it might be hard to see, but he's got a lexer and a parser in here too that he has. So that might be an example of something that you might need to create your own language for. So here's another question I'm sort of expecting. And that's, so is it like actually faster? And again, this kind of depends on what you mean, right? So my goal was to make it faster to implement FizzBuzz. So if that's your question, then yes, it's faster, right? It's shorter, it's significantly less characters. It's so short that you could put it in a tweet, and you would still have room for hashtags and hand claps. But maybe your question is it faster to evaluate FizzBuzz? Like maybe you came to this talk and you really wanted some like super high performance FizzBuzzing, right? So again, actually the answer is yes, and this is kind of thanks to R Python. So here's our slow, naive implementation, and I'll call FizzBuzz on the number 1 million, which is a lot of fizzes. And here's our divspill implementation. And with some extremely rudimentary benchmarks, it kind of seems like maybe it's not the fastest FizzBuzz, but it's definitely faster than our elementary solution. So yeah, it's kind of faster. That's the end of the talk. I just wanted to give a quick shout out to PromptWorks, who sponsors me being at this conference and a bunch of other things. And a shout out to the PyGotham organizers and volunteers and all of you for coming to the talk. Thanks a lot. I think we have like a couple minutes if anyone wants to ask a question out loud. If not, I'll be around and in the hallway. Yeah.
So if we wanted to embed something like this in a larger system written in regular Python, would we use the PLY version or could we use the RPLY?
Yeah, so rply is kind of just for creating a binary that will evaluate your language. So
it actually makes a binary.
Yeah. So there's a divspill binary that you can use to run divspill programs, which isn't super useful, but it's kind of like a proof of concept. And you could take that and turn it into something that is similar to the Python interpreter, right? And use it to parse your own language. For embedding, I'm not super sure. There are definitely some tools that would help you do that. Yeah. Any other questions? Yeah. No, this is just sort of like a toy, right? So our Python is used for PyPy, which is self-hosted Python, and it doesn't have a whole lot of use cases beyond that. So this is kind of just a toy. I don't really have a use for writing another language, but it's hard, trust me. But it's good for little fun projects and toys like this. You should try it. All right, thanks, guys.